Let's spend the next few moments talking about nucleophilicity and solvent effects. If we look at the term nucleophilicity, that refers to the rate at which the reaction will occur, or at which the nucleophile will attack an electrophile. And we say attack, but really react with is also perfectly reasonable. An electrophile, and I'll use E plus to indicate electrophile in this case. And so there's a couple of different things that tell us that we have a good nucleophile. The presence of charge typically indicates that we might have a good nucleophile. We can compare water with hydroxide. The better nucleophile is hydroxide, and that's because it has a negative charge. It makes it a better nucleophile. It's more reactive towards electrophiles. Another indication of a good nucleophile is the polarizability. Of a molecule or ion. And as we learned in general chemistry, polarizability increases with increasing atomic size. So if we look at H2S versus H2O, we know that sulfur is in the third period, whereas oxygen is in the second period. So sulfur is larger, it has more electrons, it has greater polarizability. So the better nucleophile out of these two options would be H2S, hydrogen sulfide. Because the sulfur is larger, I like to think of it as having longer arms, it has greater reach, it can more easily interact with an electrophile. The same thing if we make these into anions. We could have SH minus versus OH minus. And while OH minus certainly is a good nucleophile, SH minus is a better nucleophile, again because of the polarizability of the sulfur. Let's look at solvent effects on the SN2 reaction now. We're going to focus on two types of solvent, polar protic and polar aprotic. And of course, there are other types of solvents, non-polar solvents like hexane or pentane. These are solvents that just have C's and H's in them. They're non-polar. Those are not very useful for these substitution reactions because they don't dissolve ionic species. And as we've learned, the nucleophile is typically charged. The electrophile might have a polar bond in it, might have a dipole moment, which makes it a good electrophile. So we want things that can dissolve ionic or polar species. So polar solvents are going to be that. And so we're going to differentiate our polar solvents into two different categories. Polar protic is a solvent that has an OH bond or an NH bond. Here are two quick examples. Ethanol or ammonia. Basically, they have the ability to hydrogen bond. So if your solvent can do H bonds, you have a polar protic solvent. Polar aprotic solvents do not have NH or OH bonds. So an example here would be acetone or DMF is another example. This one confuses students initially because in DMF we tend to draw the H as part of the aldehyde. And that's great, but that H is attached to a carbon. It is not attached to an O, it is not attached to a nitrogen. So therefore, it is not a protic solvent. This is still an aprotic solvent. And scientists have found that polar aprotic give a faster rate for SN2 reactions. And you can check out the table of rates in your textbook. I'm not going to reproduce that here, but let's go to the next slide and discuss a little bit about why we might get a faster rate with a polar aprotic solvent. I'm going to use ethanol again like I had on the previous slide, and I'm going to use acetone for my aprotic. And let's use our nucleophile as NaOH. So if we look at the protic solvent, we know that the hydrogen attached to the O has a delta plus on it, and that of course can hydrogen bond with other oxygens within the solvent, so ethanol can hydrogen bond with itself, or if we have an anion present, as we would if I dissolved NaOH into my solvent ethanol, I would have a negative charge here. So that H can stabilize that negative charge, and we can have other H's from other ethanols also helping to stabilize that negative charge. I can draw a bunch more, but you get the picture. And then we have the sodium ion from our NaOH, which can be stabilized by the delta minus of the oxygen. Every time we have a delta plus on an H in a hydrogen bonding solvent, we also have a delta minus on the oxygen. And so I can draw stabilization from that O to the sodium. And I can draw other stabilizations as well from other ethanol molecules. You get the picture. So we are stabilizing anions and cations with this polar protic solvent. And as we are going to focus or stress many times in this class, more stable equals less reactive. We saw that in the acid-base chapter, where we had an anion that was more stable, that was a less reactive conjugate base, which meant that the conjugate acid of that anion was a more reactive acid, a stronger acid. So as we've seen many times this semester, and we will see in the future, more stable equals less reactive. So this polar protic solvent that I've drawn up here, this ethanol, is stabilizing both the OH-, making it less reactive, and it's stabilizing the Na+, which in a substitution reaction, the cation typically is not that important, it's just along to balance the charge. The important part here is that we are stabilizing the OH-. Let's look at how NaOH might interact with an aprotic solvent like acetone. And you can do the same analysis with many of the other aprotic solvents, again listed in a table in your book. So acetone is polar. We know that the O has a partial negative charge. The carbonyl carbon has a partial positive charge. And so that partial negative charge O, just like we saw with ethanol, can stabilize the sodium cation. And we can get stabilization from more than one acetone on that sodium cation. However, I'm going to switch to red now. This delta plus here is too sterically hindered. To stabilize anions. So the OH-, that's part of our original compound that we dissolved in acetone, will float around unstabilized, not stabilized. And as we saw over here, more stable equals less reactive. What do you think less stable is equal to? More reactive, sorry. So by not stabilizing the OH-, the aprotic solvent causes that to be a better nucleophile, a more reactive nucleophile, and it will react with the electrophile faster and easier. And we can look at this from an energy diagram standpoint. Here is the stabilization from maybe the protic solvent. That's the energy of our nucleophile. And if we were to look at the energy of the nucleophile in an aprotic solvent, we would see that it's higher. And thus, we can look at the difference in the activation energies between each of these levels, right? The aprotic solvent with the less stable nucleophile has a smaller activation energy. Thus, the reaction, if we start here, should be easier to achieve the product. compared to if we start at this position in the more stable situation with the protic solvent. So here you can see an energy diagram rationalization as to why the aprotic solvent causes faster rate in an SN2 reaction.